In this video, we're going to look at how to solve a few examples on weak acids and weak bases. Before we're going to look into those examples, over here, a very quick reminder that the pH value can be calculated by using this formula in which pH equals to negative log times concentration H plus, and the pOH value can be determined by using this formula. And when you have the value of pOH, you can use that value to figure out what is the value of pH of the solution by using this relationship over here between pH and pOH. But for weak acids and bases, it's not going to be as straightforward as solving strong acids and strong bases. To solve problems regarding to weak acids and bases, we have to use the ICE table. This is a table. This is an approach that we have looked into when we learned about chemical equilibrium. So you can guess that for weak acids and bases, we're dealing with something at equilibrium. The reason why we want to use ICE table over here is because, like I said, weak acids and bases, they tend to exist at equilibrium, and they work in terms of, it's very important for you to remember that, because now we're dealing with acids and bases, so your ICE table will be working in terms of either concentration, or sometimes you're going to use mole, depending on the situation that is given to you. Why weak acids and bases use ICE? We have talked about this just now, because they are partially dissociated in aqueous solution, so they would exist in so you would expect that we're going to use this reversible arrow in your balance equation. So this is the reason why we're going to use ICE for weak acids and bases, because they are partially dissociated. Unlike strong acids and bases, they are fully dissociated, and we can assume that your concentration of your strong acids and base can be directly corresponding to the concentration of H plus and OH minus. Now, when you look at the example here, you have this weak acid dissociated in aqueous solution, partially dissociated, so they will exist at equilibrium. And when they have equilibrium, they will have K value. But instead of writing Kc, we're going to write Ka. Ka over here is your acid dissociation constant. For base, as you can see, you have this dissociation happening right here, exists at equilibrium. For base, it will have Kb value, your base dissociation constant. So we have to remember what we have looked at in the previous video before we reach here. Ka, like I said, this one is your acid okay, and then your Kb is your Important notes on Ka and Kb. It's very important for you to know this. So when let's say Ka is higher, what happens to the strength of acid? Strength of weak acid is higher. Why? Because when you look at your equation here, how do you write Ka? So Ka is written as the same like how you have done before for Kc, is going to be written as concentration H plus times concentration of the negatively charged species over concentration of your weak acid. So if you have more of this concentration being produced, you will surely going to have bigger Ka value because you have bigger value on top. If you have less value on top, but more value at the bottom right there, you will have smaller Ka. So if you have less concentration of H plus, that means your weak acid is not really strong. Your weak acid is very, very weak. The strength of that weak acids is lower if you have lower amounts of H plus being produced. So when you have lower amount of H plus being produced, automatically your Ka value will be lower. So that's why when you have Ka value higher, the strength of your weak acid will be higher. So when your Ka value is smaller or lower, the strength of weak acids will also going to be weaker. So this is very, very important. Same goes to your base. If you look at your base, you'd have concentration of OH minus on top, divide times by concentration of the positively charged species over concentration of NH3. So we're not going to be including your water molecule because that one is your pure liquid. Remember, pure liquid and solid will not going to be part of your dissociation constant K. Same goes to your base. If you have more OH minus being produced, means your weak base will be stronger. Okay, so if you have more of this, your Kb value will be higher. If you have less of OH minus, your Kb value will be smaller. So the strength of weak base will be lower. Okay, so I'm going to write that here. Okay, so that is the relationship between Ka and the strength of weak acids, Kb and the strength of weak base. So another thing that you need to know is sometimes the question they're going to give you in terms of pKa or pKb. Sometimes they're going to give you in terms of this. So what is that? So basically, what we have right here is we have Ka value and we have pKa value. pKa value is negative log times the value of Ka that we have here. So pKa is just the inverse of Ka. Okay, same goes to pKb. They're going to give you Kb value. So pKb is simply the negative log times to the value of Kb. Okay? So if you have this situation, it will be the opposite in terms of relationship of the strength. So if you have when pKa higher, strength would be lower. Okay, same goes to this. When pKb is higher, strength would be lower as well. So it's the opposite. So when you have value of pKa or pKb given to you instead of Ka and Kb, the relationship between the strength of the weak acids over here and the weak base over here will be the opposites. If you have bigger pKa for a certain weak acids, that means the strength of the weak acids will be smaller when you have bigger pKa. When you have value of pKb that is bigger, okay, pKb, notes that pKb, same like pKa right there. If you have value of pKb higher, the strength of your weak base will be lower. So it's different than what we have for Ka and Kb. Note that. Always remember that. Now let's have a look at how to solve a few problems regarding to weak acids. Remember, for weak acids and bases, we're going to use the ICE table to solve this. This is a very typical question for weak acids, and acetic acid, CH3COOH, is the most classic example for weak acids. So you might gonna see this in exams. They like to use this. Acetic acids is your common weak acids. You have this in your restaurant. They sell it in the shops, and you might even have this at your home. This is your vinegar. Okay? Now, how do I know that acetic acid is a weak acid, even without the question mentioning that it is weak acid? So this is a trick. When you have a question in exams and you don't know whether it's going to be weak or strong, you have to look for the value of Ka. If the value of Ka is given, for example here, the question gives you the value of Ka. I know that the value of Ka is given, so from there, this is the clue that it is a weak acid. So when you see Ka value is given, automatically your brain needs to switch to the ICE table. Okay, so you cannot just use pH equals to negative log times concentration of H plus to find the pH that we want to find over here. Okay, I know it's very tempting for you to do that because you have the concentration of the acid is given and then they want you to find pH. Okay, and the question doesn't say that this is a weak acid explicitly. It doesn't say right away. But how do you know it's going to be weak acid? Like I said, look for the clue. And what is that clue? It's right here. The value of Ka is given to you. Only weak acids and bases will have value of Ka and Kb that is significant. So this is the clue, remember. Now, that is one. Second, we know that the question wants you to find pH, and now you have degree of dissociation. So the question wants you to find two things. You need to find pH, so you're going to use negative log concentration H3O plus, and you have degree of dissociation. So degree of dissociation is, remember, concentration of your change over concentration of initial. So you have to remember this. This is what we have learned in chemical equilibrium. You can check out the video for degree of dissociation. It's going to be the same concepts that we're going to use in here. The only difference that we're dealing with acids, that's all. Okay. To find the value of pH, we need to know what is the concentration of H3O plus. And to find the, to get this concentration, we have to use the ICE table. Okay? And before we want to produce your ICE table, note that in this question, it doesn't give you the balance equation. So the first thing you need to have, okay, step number 1 is to write your balance equation, which is CH3COOH aqueous solution plus water, and you'd have H3O plus aqueous plus CH3COO minus aqueous. So this is the first thing you need to find out. So what is the balance equation involved? The reason why we need to have a balance equation, because your ICE table later will be highly depending on your coefficient. If you still remember, when we do ICE table in the change section, you have to get the right coefficient in front in order for you to find the value of X. Okay, so by writing this balance equation, you get 1 mark. So let's have a look at the ICE table. Again, why do we want to use ICE table? Because we want to find out what is the concentration of H3O plus. Like I said, for weak acids and bases, it will not going to be straightforward as what we have done for strong acids and bases. We cannot just take the concentration right here right away and plug that into there. We have to use the ICE just like this. So now the ICE that we're going to be using is for concentration. Okay. And then note that this is in liquid, pure liquid. So that one will be ignored. We're not going to be dealing with that one. And what is the initial concentration of acetic acids? So the initial concentration is 0.015 right there, 0.015. So we're going to fill that in. So this is 0.015. And we don't have this being produced yet. This one as well. So by writing this correctly, you get another 1 mark. And what about the change? Remember, this is 1 mole. 1 mole, so you have negative X, because this is your reactant. So reactant will be decreasing in concentration, hence the negative sign in front of your X. And then this one is plus X. This one is plus X as well. So at equilibrium, we have 0.015 minus X. This one is X, and that one is X. You'll get 1 mark for that one, 1 mark for that section right there. Okay, next what we're going to do is we're going to write the Ka expression. So you need to remember, you need to write the Ka expression for the reaction on top. So the Ka expression would be concentration of H3O plus times concentration of CH3COO minus divide by concentration of CH3COOH. So by writing this, you'll get another 1 mark. So another very important characteristic for the calculation over here, we have an assumption that you need to do, and it's very, very important. Okay, but before we're going to do that assumptions, remember, try to plug in all the values inside. So that one, you're going to plug in X into there, and that one inside. So you'll get this. Okay, so I have plugged in the value inside there. So what did I say about assumption just now? So there's a very, very important thing. Remember the Ka value given. The given Ka value is 1.8 times 10 to the power of negative 5. This is given in the question. Okay, it's right there. It's right over here. So what you need to do now, since we can consider that this Ka is very small because it is to the power of negative 5. This one is to the power of negative 5. Therefore, we can consider this one is very small. We can assume that this Okay, this value over here is 0.015 minus x. Is approaching to 0.015. So by writing this assumption, you'll get another 1 mark. So when you have this assumption now, in the beginning, we have Ka equals to x squared minus 0.015 minus x. This is what we have in the beginning, right there. But after we have done this assumption, based on the Ka value that is given to you, we can assume that this value is approaching to 0.015. So you can change this to 0.015. Okay, so to solve this, Ka 1.8 times 10 to the power of negative 5 equals to x squared over 0.015. So now your x squared would be 2.7 times 10 to the power of negative 7. And the value of x, you can have one value only, which is 5.196 times 10 to the power of negative 4. So you get the value of x right here. So if you look at your ICE table, the concentration of H3O plus is equals to X. Concentration of H3O plus is equals to X. And x value now is this, 5.196 times 10 to the power of negative 4 molar. Now we have found out the concentration of H3O plus. So you get another 1 mark right there. So when we have found the concentration of H3O plus, then we can plug that value into this pH equation to find the pH of your acetic acid. Okay? Therefore, of your acetic acid, CH3COOH, is pH equals to negative log. Then we can plug in the value just now, which is 5.196 times 10 to the power of negative 4. And the pH would be 3.3. So you get 1 mark for this, and you get 1 mark for that one. So what about the degree of dissociation? So we have solved for, we have done for this, we have done for that one, What about degree of dissociation? Remember, degree of dissociation is defined as this. So we have to go back to your ICE table. So degree of dissociation is change over initial. Okay. So for the degree of dissociation, always remember, so this is the part that we're going to look at. We're going to look at over here for degree of dissociation. For dissociation, so it will be concentration of change over concentration of initial. The change that we have, what is the value of x? Remember, change is defined as x here. That is the change. And the value of x is this. So we're going to plug in the value, that one. So we have 5.196 times 10 to the power of negative 4. And the initial is 0.015. So degree of dissociation is about 0.035. So you'll get 1 mark for this and 1 mark for that one. Right. Now, let's have a look at the second example for weak acids. In this question, it wants you to find the acid dissociation constant, and you have degree of dissociation. Another clue, how do you know that this one will be dealing with weak acid, or maybe it's going to be a strong acid? How do you know that? If just now we're going to look at the value of Ka given right here, the clue is just right there. Acid dissociation constant. You need to find it. So when you need to find the Ka, okay, from here, so this is the clue. Clue for weak acid. Why? Because we need to find Ka. And to find Ka, we have to use ICE table. Okay, that's very important. To find your Ka, you need to use your ICE table. And the question gives you this. Degree of dissociation. Degree of dissociation of 0.10 molar weak acids is 3.5. Okay, degree of dissociation is 3.5%. Okay, so question gives two things. It gives you the molarity of the acid, okay? But the most important thing over here is the degree of dissociation. Degree of dissociation. Or you can change that into 0.035. So the first step that we need to do is to write the balance equation of HX. So we don't know what is this. So HX aqueous plus H2O liquid. And you're going to be producing H3O plus aqueous plus X minus aqueous. So this is the balance equation we need to have together with the ICE table that we're going to be constructing later on. Having this balance equation written, they're going to give you 1 mark. So your ICE table will look like this. Remember, that one is your pure liquid. So pure liquid will not going to be part of the ICE table, nor going to be part of the Ka. The initial concentration for HX is given, which is 0.10 molar. So this is the initial concentration of the weak acid. So that is the initial concentration of the weak acid. Okay. So we're going to plug that into here. 0.10. This one is not being produced yet initially. Change negative X plus X plus X. Equilibrium 0.10 minus X. This one is X, that one is X. For this, you're going to get 1 mark. This one, you're going to get 1 mark. This one, you're also going to get 1 mark. Okay. Now we're going to find what is the value of Ka. We do know that Ka is written as this. This is the Ka expression for this weak acid. And when you plug in the value, inside there, okay, you get X squared over 0.10 minus X. Now the question is, how are we going to find the value of X? If we can get the value of X, we can plug in the value here and to find the value of Ka. So what does the question give to us just now? We have degree of dissociation. Degree of dissociation. Okay, so degree of dissociation is defined as concentration of change over concentration of your initial. So when you look at your ICE table, remember, this is the part where we're going to look at for degree of dissociation. And then over there, we can find X. Okay? So From the ICE table, the degree of dissociation is x over 0.10. And the question gives degree of dissociation equals to 0.0. If we go back to the question, 0.035. So you're going to compare this with that. You have 0.035 equals to x over 0.10. Therefore, x, the value is 3.5 times 10 to the power of -3. So that is the value of x. This is the value of x that we want. Okay, by doing that, you're gonna get another 1 mark. So we take the value of x that we have found right there, and we're gonna plug into the Ka expression. So the Ka value is, just now we have Ka equals to x squared over (0.10 minus x). So we're just going to plug in the value. (3.5 times 10 to the power of -3 square over 0.10 minus 3.5 times 10 to the power of -3, and the Ka value that you will get is 1.3 times 10 to the power of -4. Okay, so you get 1 mark. So the difference that we can see between this problem and the problem that we have done right here for this question, because Ka value is given, Ka value, we know what is the Ka value. That is the reason why we can make this assumption, because we know what is the Ka value. However, for this question, we need to find what is the Ka value. So we don't know whether the Ka is going to be big or whether it's going to be small enough for you to assume. So that is the reason why, if you look at your work right here, all the way down to right there, we do not have the assumptions. Okay? Why? Because we need to find Ka, because we don't know what is the value of Ka. And as you can see, the value of Ka is -4. So if you have to the power of -4 here, you cannot do any assumptions for this kind of Ka. Okay? So the tip that I can give to you, if the question wants you to find Ka, do not assume. So one tip over here. if the question wants to find Ka or Kb, do not assume. Okay, so that's a very good tip. If the question wants you to find Ka or Kb, if the question gives you Ka or Kb, then you have to look at the value first. Is it very small? Is it not small enough for you to assume? Now let's have a look at weak bases. We have ammonia been given to you, solution. It doesn't say that it's going to be a weak base explicitly, but if you look there, you have the Kb value given to you, and it is to the power of -5. So we can do some assumption. When you have this kind of situation, then we can have some assumption that we have to do. Okay, so what does the question want? Okay, before that, I'm just going to highlight. This is the clue. Okay, so this is the it's a clue for weak base because Kb value is given. And then when you look at the value here, you have to the power of -5. Then you can guess that in your step afterwards, you're going to have some assumption that you need to do. The question wants you to find degree of dissociation. So questions want you to find degree of dissociation. Therefore, we need to find the concentration of the change divided by concentration of the initial. Initial of what? This 0.40 molar of ammonia solution. So we need to find your ICE. Because of this, okay, we need to construct your ICE. Now, first step. Step 1, we need to write the balance equation for ammonia dissociation. We have NH3 aqueous, okay, and then you can add water if you want, but it doesn't really matter. If you don't have water, that should be okay. Then you have NH4 plus aqueous plus OH minus aqueous. So this is the balance equation that you need to have. So by writing that balance equation, you get 1 mark. Now let's have a look at this balance equation with the ICE table. You have your balance equation written on top. Okay, and this OH minus comes from the H2O liquid that lost one of the protons, and the proton is given to you NH3, becoming NH4 plus right there. So, as usual, pure liquid will not gonna be part of the ICE, and also it's not gonna be part of the Kb. And what is the initial concentration of ammonia given to you? So the initial that is given to you is 0.40. We don't have this one yet being produced in the beginning. And the change, we have to look at your balance equation. You have 1 mole of NH3, therefore you have negative X for the change. You have 1 mole of OH minus, therefore you have plus X. This one is also plus X. And at equilibrium, 0.40 minus X. This one X, and that one is also X. Okay, so by getting this correctly, you have 1 mark, 1 mark, 1 mark for each of the section. Next, what we need to do is we need to write the KB expression, because we want to find out, our mission is to find the change. We know the initial already, okay? We know this initial is equals to this, but what is the change? Remember, to find the degree of dissociation. Degree of dissociation, we need to look at this part. Okay, this is the part where we're going to look at for degree of dissociation. We know that the initial is this, and we want to know what is the value of X. And the question gives you KB value. So when you have KB value, we can use that to find the value of X. So the next thing that you need to do is you need to write the KB expression is going to be concentration of OH minus times with concentration NH4 plus over concentration of NH3. Okay? And then when we plug in the value in there, this one into that one, and 0.40 minus X to the one right there, you should be getting KB value that will look like this now. X squared over 0.40 minus X. So by writing this, you get another 1 mark. We have the value of KB given, so we're going to plug in the value of KB right here. Okay, the value of KB is 1.8 times 10 to the power of negative 5, and this is to the power of negative 5. And yes, we will do some assumption. So the KB value is 1.8 times 10 to the power of negative 5. This is given to you in the question. Since we can assume that the 0.40 minus X will be approaching to 0.40. So this 0.40 minus X is the value for that one. So we're going to take this one or that one at equilibrium. So we'll be approaching to 0 because it is very, very small. So when you minus that, when you take this value of X, when you minus with this, the value will still going to be closer to 0.40. This assumption is very important because you will get 1 mark. When you write this assumption, you're going to get 1 mark. So after you have done the assumption, So the value of KB just now, x squared minus x squared over 0.40. Okay, so this is going to be the how it's going to look like after we have assumed. And we're going to replace the value here into your KB. You get 1.8 times 10 to the power of negative 5. X squared 0.40. So x squared equals to 7.2 times 10 to the power of negative 6. So the value of x would be 2.683 times 10 to the power of negative 3. So this is the value of x. Okay, that is the value of x. And when you look right there, we need to find the degree of dissociation. Okay, you need to find degree of dissociation. And we have the x already, so we're going to take that value. You're just going to plug in there into this equation right here. Okay. So the degree of dissociation is, the change just now is 2.683 times 10 to the power of negative 3. And the initial 0.40, then you get 6.7 times 10 to the power of negative 3. So this is the degree of dissociation. So you have 1 mark right there, 1 mark right there, and also 1 mark right there for the value of x. Right. Now let's have a look at the final one for this video. We have quite a long questions over here, but it's not going to be that difficult. What we need to do now, we need to determine the concentration of H3O plus at equilibrium. You have the word equilibrium right now. Okay, so you have equilibrium concentration of H3O plus. How do we do that? Okay, so when you have concentration at equilibrium, and then you have the base dissociation constant value, that is the clue. Those are the clue for ICE table we need to use. You have base dissociation constant value, Kb, right here, and you need to determine the equilibrium concentration of H3O plus. Okay, and also what we have is this. This is your initial concentration. Okay. So the first thing we need to do is the balance equation, which is CH3 aqueous. So you need to have water liquid, and you'll get OH minus plus CH3 3 NH plus aqueous. So this is 1 mark you're going to get for the balance equation. And we're going to plug that into your ICE table, like what I have done right here. And I have my ICE ready. Okay, now we want to find the concentration of OH minus first. If we can find the concentration of OH minus, we can find the POH value. And from the POH value, we can find the pH value. Okay, why do we need to find pH? Because we want to find the concentration of H3O plus. Okay. First thing, we need to ignore your liquid. Okay, remember that is your liquid, so you're going to ignore that. And the initial concentration is 0.15. That one is not being produced yet. This one is minus X plus X plus X, like what you have done here. 1 mole, 1 mole, 1 mole. Change 0.15 minus X, X, and X. Okay. So by writing this, you get 1 mark, 1 mark, and another 1 mark. So what about the Kb expression? We need to write the Kb expression. The Kb expression would be concentration of OH minus, concentration of your positively charged species, CH3, and then when you plug in the value at equilibrium, so we're going to take the value, because the value that we can put into your Kb and Ka is the value at equilibrium. So these are the values at equilibrium. So the same concept we're going to apply as what we have learned in chemical equilibrium before. So we're going to plug in the value here. We're going to put it in there. Then you get X squared over 0.15 minus X. So by doing this, you get another 1 mark. Now we want to find the value of X. Okay? Kb value that is given is 6.30. And as you can see, it is to the power of -5. So we can do some assumption. We can safely assume that this value, okay, is approaching to 0.15. Minus X is approaching to 0.15. Okay, so it's a very, very important assumption. You have 1 mark. Right. Now the Kb expression will look like this. X squared over 0.15. So when we plug in the value of Kb, 6.30 times 10 to the power of negative 5 equals to x squared. You have 0.15. So x squared would be 9.45 times 10 to the power of negative 6. X therefore is 3.1 times 10 to the power of negative 3. By doing this, you'll get another 1 mark. So we do know that from the ICE table, X value here is also the concentration of OH minus from the ICE table. So I'm going to write from the ICE, we know that concentration of OH minus is equals to X. And then this X is right there. So we have found out the concentration of OH minus as well. So concentration of OH minus is 3.1 times 10 to the power of negative 3 molar. By writing that, you'd get another 1 mark. However, the question wants you to find concentration of H3O+. We have found the concentration of OH minus. So how do we do that? Okay. So how do we find how to get concentration of H3O+ from concentration of OH minus? So that is the question. So how we do that? First, we have concentration of OH minus already, which is 3.1 times 10 to the power of, which is this. So we're going to use this. We're going to use that one. Okay. We can find POH first. So you're going to plug in the value of your concentration into this. Then your POH would be and the POH value is 2.51. Okay. And we're going to use pH plus POH equals to 14. We're going to use this. So we're going to find pH plus, we have the value of POH, which is 2.51 equals to 14. Therefore, pH is 11.49 and we're going to use this. Okay, we're going to use this one into your pH equals to negative log concentration H plus. Okay, so you have 11.49 equals to negative log concentration H3O plus. So you take this negative to the other side. So you have concentration H3O plus equals to inverse log negative 11.49. Okay. So what is that value? So you get the value is about 3.24 times 10 to the power of negative 12 molar. Okay, so that is the answer right there. So you'd get 1 mark for this, 1 mark for that, 1 mark for the final answer, 1 mark for this one, and 1 mark for your pH equals to negative log concentration H3O plus.